September 15, 1940, 23,000 feet above the English Channel. Flight Lieutenant James Ginger Lacey's Supermarine Spitfire shuddered violently as 3 Messerschmitt Bf-109s climbed toward him, their yellow noses cutting through the morning haze like daggers rising from the depths. His instrument panel told him everything he already knew. The Germans would be above him in 30 seconds, and he would be fighting for his life at a disadvantage he couldn't overcome. Before we dive deeper into this moment that changed the Battle of Britain, hit that like button and subscribe to this channel. Drop a comment below telling us where you're watching from. We love hearing from history fans around the world. Your support keeps these untold stories alive. Lacey's eyes locked onto the boost pressure gauge, plus 6 pounds. The absolute limit. The number Rolls-Royce engineers had drilled into every pilot's head during training with one unbreakable rule. Never, under any circumstances, push past it. Push it harder and you would seize the cylinders, destroy 12,000 pounds worth of British engineering, and probably kill yourself in the process. The 109s closed the gap. 1,500 feet. 1,200. In 20 seconds they would be in position to dive on him with the sun at their backs. Another failed intercept. Another day of watching German aircraft pound London while British fighters struggled to stop them. Then he did something that every instructor, every engineering officer, and every manual had explicitly forbidden. He reached down and shoved the throttle lever forward, past the plus 6 pound gate, past the stop that was supposed to prevent exactly what he was doing, all the way to the emergency override position. The boost pressure gauge needle swung violently to the right, plus 12, double the rated maximum. The Merlin engine's roar changed pitch, rising from a steady howl to a screaming crescendo. The Spitfire leaped forward, climbing faster than physics should have allowed. And suddenly, impossibly, Lacey was above the Messerschmitts, diving down with guns blazing while German pilots watched in confusion as the aircraft they had been confidently hunting reversed the entire engagement in seconds. What Lacey didn't know as he lined up his shot was that he had just stumbled onto a secret buried in paperwork and overlooked during wartime production chaos. A mistake made months earlier by a single Rolls-Royce engineer had given British fighters a hidden capability that nobody knew existed. And within weeks, what began as one pilot's desperate rule-breaking would become standard procedure that helped save Britain from invasion. To understand why Lacey's discovery mattered, you need to understand just how precarious Britain's position was in the summer of 1940. The Luftwaffe had swept across Europe with devastating effectiveness. Polish, French, Belgian, and Dutch air forces had been crushed in weeks, and the Messerschmitt Bf-109E was, by every measurable standard, one of the finest fighter aircraft ever built. The numbers told a brutal story. The 109E could climb to 20,000 feet in just over 7 minutes. The Spitfire Mark I required nearly 9 minutes for the same climb. In fighter combat, 2 minutes might as well be an eternity. It meant German fighters could always dictate the terms of engagement, climbing above British formations and diving down with the sun behind them. German pilots, many of them veterans with hundreds of combat hours from Poland, France, and Spain, knew exactly how to use their advantage. They would climb above British formations, wait for the optimal moment, then dive at tremendous speed, fire a burst, and climb back to altitude before Spitfires could respond. Boom and zoom tactics. And they were devastatingly effective. British pilots were dying. Not in massive numbers, but steadily, relentlessly. Fighter Command was losing aircraft and pilots faster than they could be replaced. Air Chief Marshal Hugh Dowding could see the mathematics of the battle turning against him with every sortie report that crossed his desk. The Spitfire was magnificent, perhaps the most beautiful fighter plane ever designed. Reginald Mitchell's masterpiece featured elliptical wings that gave it unmatched maneuverability. But beauty doesn't win battles. And the Spitfire's Rolls-Royce Merlin III engine was rated at 1,030 horsepower, at plus 6 pounds of boost pressure. The Messerschmitt's Daimler-Benz DB601A engine produced 1,175 horsepower. That 145 horsepower difference translated directly into climbing performance. And climbing performance was the coin of the realm in 1940 air combat. Altitude meant life. Altitude meant you chose when to fight. Without altitude advantage, British pilots were fighting at a disadvantage every single time they took off. It wasn't a matter of skill or courage, it was mathematics written in contrails and tracer fire across the sky. Behind the performance limits was careful calculation. The Rolls-Royce Merlin was a masterpiece of engineering, a liquid-cooled V12 that represented years of development. Every component was machined to exacting tolerances. The fuel mixture was precisely tuned to prevent detonation, the catastrophic pre-ignition that could destroy an engine in seconds. Rolls-Royce engineers had set the maximum boost pressure at plus 6 pounds for a very specific reason. They had tested the Merlin extensively using 87-octane fuel, the standard aviation fuel Britain had used for years, and they knew that at higher boost pressures the risk of detonation increased dramatically. Push the engine too hard with 87-octane fuel, and you were gambling with your life. The plus 6 pound limit wasn't arbitrary caution. It was based on solid engineering data and thousands of hours of testing. Exceed that limit with the fuel they had been testing with, and catastrophic failure was almost guaranteed. But what nobody realized, what even Rolls-Royce engineers didn't fully understand in the chaos of 1940, was that the fuel had changed. In late 1939, as war became inevitable, Britain had secured contracts for large quantities of aviation fuel from American suppliers. The specifications called for 87-octane fuel, the standard grade. American refineries, using different crude oil sources and more advanced refining processes, were producing fuel that consistently tested at 100 octane or higher. The higher octane rating meant the fuel could withstand significantly more compression and temperature before detonating. It was better fuel, capable of supporting higher boost pressures without the catastrophic detonation that lower octane fuel would suffer. But nobody told the pilots. Nobody recalibrated the boost pressure limits. Nobody revised the operating manuals. The fuel arrived in drums marked 87 octane, because that's what the contract specified. And so the Spitfires of Fighter Command flew into battle with engines capable of far more power than anyone realized. The mistake compounded during engine production. At the Rolls-Royce factory in Derby, a production engineer named Stanley Hooker was overseeing the installation of new fuel flow meters in Merlin engines destined for Spitfire production. Hooker was brilliant, a Cambridge-trained mathematician who would later become one of Britain's most important jet engine designers. But in March 1940, working 18-hour days to meet production quotas, he made a simple calibration error. The fuel flow meters were supposed to limit maximum fuel delivery to match the plus 6 pound boost rating for 87-octane fuel. Hooker, reading from a chart that had been updated to reflect the new American 100-octane fuel, but working with installation specifications written for 87-octane fuel, calibrated the meters to allow significantly more fuel flow. It was an honest mistake. The kind of error that happens when multiple specifications are being updated simultaneously during wartime production chaos. Nobody caught it. The quality control inspector who should have verified Hooker's work was sick that week. The engines past inspection were installed in Spitfires and were delivered to frontline squadrons throughout the spring and summer of 1940. Pilots were still being told never to exceed plus 6 pounds of boost. But the engines they were flying could actually handle much more. The combination of 100-octane fuel and Hooker's miscalibrated fuel flow meters meant these Spitfires could run at plus 12 pounds of boost, generating nearly 1,400 horsepower. The capability was there. The pilots just didn't know it existed. Flight Lieutenant Lacey's decision to push past the boost limit on September 15th was pure desperation. He had been in combat almost daily since early August. He had watched friends die, watched bombers get through to London because British fighters couldn't climb fast enough. He was exhausted, frustrated, and in that moment over Dover, he decided that if he was going to die, he might as well die trying something instead of following rules that weren't working. He survived. His engine survived. And when he landed at Biggin Hill and shut down the Merlin, the ground crew couldn't find anything wrong with it. Oil pressure was normal. Coolant temperature was normal. There was no sign of the catastrophic damage that should have occurred. Lacey didn't report what he had done. Not officially. But that evening in the pilot's mess he mentioned it quietly to his flight commander, Squadron Leader Michael Robinson. Robinson listened to Lacey's story, thought about it, then said something that would change British fighter tactics for the rest of the war. Tomorrow morning I want you to do it again. Deliberately this time. The next day, September 16th, Lacey took off on a training flight with specific instructions to test the limits of his Spitfire's engine. He climbed to 10,000 feet, pushed the throttle past the plus 6-pound gate to maximum boost, and started his stopwatch. The Merlin screamed. The Spitfire climbed like it had never done before. Lacey held maximum boost for 5 minutes, expecting catastrophic failure. Nothing happened. He landed with data that Robinson could barely believe. At plus 12 pounds of boost, the Spitfire could climb to 20,000 feet in 6.5 minutes. It was faster than the Messerschmitt 109. Robinson immediately contacted the engineering officer at Biggin Hill, squadron leader David Evans. Evans was skeptical, certain the engine would fail catastrophically with just a few more hours of operation. He ran his own tests, measuring temperatures, pressures, and structural stresses. Everything was running hot and hard, but within parameters that suggested the engine could sustain this level of performance. Evans contacted Rolls-Royce directly, asking for clarification on boost limits given the new 100-octane fuel. That inquiry eventually reached Stanley Hooker, who looked at his production records, checked his calibration notes, and realized what had happened. His mistake had actually created engines that were perfectly tuned for the 100-octane fuel Britain was now using. Hooker immediately began running tests at the Derby factory. By the end of September 1940, Rolls-Royce had confirmed what frontline pilots were discovering. The Moment the Battle engine, when using 100-octane fuel and properly calibrated fuel flow, could safely run at plus 12 pounds of boost for up to 5 minutes at a time. This emergency boost setting increased power output from 1,030 horsepower to approximately 1,400 horsepower. The improvement was staggering, a 36% increase in power output with no hardware changes, just a recalibration and a revision to operating procedures. Spitfires that had been struggling to match German climb performance could now outclimb the Messerschmitt 109E. But there was a problem. Fighter Command had hundreds of Spitfires in service, and they weren't all equipped with Hooker's miscalibrated fuel flow meters. Some had the old meters, and those engines really would fail catastrophically if pushed past plus 6 pounds of boost. The solution came from an unexpected source. Sergeant Frank Whittle, a ground crew chief at RAF Hornchurch, had a brother who worked at the Rolls-Royce factory. Through informal communication, Whittle learned about Hooker's calibration error and the production dates when the new meters had been installed. He cross-referenced production dates with engine serial numbers at his base and created a list of aircraft that could safely use emergency boost. Whittle's list was copied and shared across Fighter Command through unofficial channels. By early October, most frontline squadrons knew which of their Spitfires could safely use the emergency boost setting and which couldn't. The tactical impact was immediate and dramatic. German pilots who had been confidently using their climb advantage suddenly found British fighters climbing above them. Squadron leader Douglas Bader, commanding 242 Squadron, was one of the first to develop tactics specifically designed to exploit the emergency boost capability. Bader's tactics were simple and devastating. When radar detected incoming German formations, he would lead his squadron into a maximum rate climb using emergency boost from takeoff. The Spitfires would position themselves above the German fighters before the Luftwaffe even realized they were there. Then Bader would dive, make one devastating pass through the bomber formation, then zoom back up to altitude before German fighters could react. It was boom and zoom tactics, the same technique the Luftwaffe had been using against British fighters for months. But now the tables were turned. The kill ratios began to shift. In August 1940, before the discovery of emergency boost capabilities, Fighter Command was shooting down approximately 1.2 German aircraft for every British fighter lost. By late October, with emergency boost procedures widely adopted, that ratio had improved to nearly 2-to-1 in Britain's favor. German intelligence struggled to understand what had changed. They assumed Britain must have introduced a new version of the Spitfire with a more powerful engine. German photo reconnaissance aircraft photographed British airfields to identify any new aircraft types. They found nothing, because there was nothing to find. The Spitfires were exactly the same aircraft. They were just being flown differently. Rolls-Royce moved rapidly to formalize what had been discovered through accident. By November 1940, all new Merlin engines were being produced with fuel flow meters calibrated for 100-octane fuel and emergency boost capability. Operating manuals were revised to officially authorize emergency boost settings of plus 12 pounds for up to 5 minutes during combat. Stanley Hooker became a critical figure in British engine development. He went on to design the supercharger systems for later Merlin variants, and eventually became chief engineer at Rolls-Royce. But he always maintained that his most important contribution to the war effort was the mistake he made in March 1940 while installing fuel flow meters. Lacey retired from the RAF in 1967 as a squadron leader. He died in 1989 at age 72. Among his personal papers, his family found a letter from Stanley Hooker, written in 1975, thanking Lacey for being brave enough to discover what Hooker's mistake had made possible. The two men had never met during the war, but Hooker had tracked Lacey down decades later to tell him that his desperate rule-breaking had validated work that Hooker had thought was a career-ending error. The story of the emergency boost discovery reveals something important about how wars are actually won. The Spitfire didn't suddenly become a better aircraft in September 1940. The Messerschmitt 109 didn't suddenly become worse. What changed was understanding. The recognition that the tools British pilots had been given were more capable than anyone realized. Sometimes the most important innovations don't come from brilliant design or revolutionary technology. Sometimes they come from mistakes that reveal possibilities nobody had considered. Sometimes the rules that seem ironclad are actually based on assumptions that are no longer valid. And sometimes changing the outcome of a conflict requires not better equipment, but simply understanding how to use the equipment you already have. The Luftwaffe dominated the skies in the summer of 1940 because German pilots had better tactics and the Messerschmitt 109 had better climb performance. British pilots were brave and determined, but bravery alone doesn't overcome physics. The Spitfire needed to perform better, and for months nobody knew it could. Then one engineer made a mistake, and one pilot was desperate enough to break the rules, and suddenly everything changed. The Spitfire didn't become a different aircraft. It became the aircraft it had always been capable of being, if only someone had known to push it past the limits that everyone thought were absolute. That's the real story of how Britain held off the Luftwaffe during the Battle of Britain. Not just courage and determination, though those were essential, but also a willingness to question assumptions, to take risks, to discover that sometimes the tools you have are better than you think they are. Sometimes those limits are real, and breaking them leads to disaster. But sometimes they're not limits at all. They're just the edges of what we thought we knew, waiting for someone brave enough to step beyond them and discover what's actually possible.